In the last two lectures, we saw the definition of a topological space and some examples. Next, we want to explain some ways which we can use to define topologies on sets. So our aim is to construct a large collection of topological spaces and then study topological properties of these spaces. So before we begin, so let us define what are open sets. Let X be a set and let tau be a topology on X. Then the sets U, which are members of tau, are said to be open for the topology tau. So next, we want to define what is a basis for a topology. So let X be a set and let tau be a topology on X. A collection P contained in tau is called a basis for tau if it satisfies the following condition. Given any open set U in tau and an element X in U, there is an element W in the basis such that X belongs to W and W is contained in U. So let us see some examples. So consider the standard topology. On R, let P be the collection of open intervals AB. Then B is a basis for the standard topology on R. So to see this, we need to check that if U is open in the standard topology, and X is in U, then there is an interval A comma B such that X is in A comma B and A comma B is contained in U. But recall that open sets in the standard topology were exactly those which satisfied the property star, which said the following: given any X in U, there is an epsilon positive such that X minus epsilon comma X plus epsilon is completely contained inside U. Thus, we may take the interval A comma B to be equal to X minus epsilon and X plus epsilon. So this proves that B is a basis for the standard topology on R. So the next example is very similar. Consider the standard topology on R2. And this time, let B be the collection of subsets of the form. These are the open squares that we define. And again, it is easily seen that B is a basis for the standard topology. Or two. And similar, so this is left as an exercise. And similar to the previous two examples, write down a basis for the standard topology on Rn. So in the above examples, we were given a topology and we wrote down a basis for this topology. So now we shall explain how to construct a topology from a collection of subsets satisfying two properties. So first, let us prove a lemma which motivates one of these two properties. Let tau be a topology on X and let B be a basis for tau. Then the union of all members of the basis is equal to the full set X. So this is easy to prove and it follows easily from the definition of a basis. So it is clear that the union is contained in X. That's because each of the W's is a subset of X. So we need only to prove the other inclusion. So we only need to prove that X is contained in union W. So to prove this, let X in X be an element. Then uh, taking u equal to x and using and the point x in u and using the property of a basis, we get that there is an element w sub x in this basis such that x belongs to w sub x, and well, this is obvious, w sub x is obviously contain x. Thus, x is in the union, w belongs to v, w. So this shows that x is contained in w. So this completes the proof of the lemma. So now we have the following proposition. And the two conditions in the proposition are motivated by properties of basis, which we saw above. So let x be a set and let B contained in P of x be a collection satisfying the following two A and the second condition is given W1 and W2 in B and an element X in W1 intersection W2, there is a W in B X belongs to W and W is contained in W1 intersection W2. So suppose we are given a subset B of the power set of X which satisfies these two conditions, then we define a subset tau of P of X to be the collection of subsets U given any X in U. There is a W in B such that X is in W and W is contained in U. So then we claim then tau is a topology on X, and B is a basis for tau. So let us prove this proposition. So to do this, let us check that tau satisfies the conditions for being a topology. The first condition is the empty set. The empty set is in tau. So this is vacuously true. The second condition is the full set X is in tau. So this is true because the full set X satisfies the property defining tau as given any X, there is W in B such that X belongs to W, and W is obviously contained in X. Right? This is because B satisfies property A, condition A, the first condition in the proposition. So thus tau satisfies condition, the first condition for being a topology. Let's check the second condition. So suppose U1, U2 up to UN are finitely many elements of tau, then we need to show that their intersection Ui is in tau. So we need to check the intersection satisfies the property defining tau. So suppose X is in the intersection of the Ui's. Then for each I, since the Ui's are in tau, there is Wi in B such that X belongs to Wi and Wi is contained in Ui. Thus, X is in the intersection Wi, which is contained in the intersection of Ui. So now we claim that property B in the statement of the proposition implies the following property B prime. Let W1, W2 up to Wn be elements of B, and let X be an element in the intersection. Then there is a W in B such that X belongs to W and W is contained in the intersection of Wi's. So the proof of B implies B prime is left is left is an easy induction argument and left to the reader and left as an exercise. Okay, so now we will simply use property B prime. Using B prime, it follows that there is W in B such that X belongs to W, which is contained in the intersection I equal to 1 to Wi, which is contained in the intersection I equal to 1 to Ui. So, so this shows that tau satisfies the second condition for being a topology. So finally, let's check the third condition. Suppose we are given a collection Ui for I in some indexing set I, and Ui is a member of tau. So we need to show that the union of the Ui's is a member of tau Ui. So we take an element X in the union, and so this implies that X belongs to Uj for some J in I. And since Uj is in tau, this implies that X is W in B such that X is in W is in Uj, and this implies that X is in W is in union of I. So thus tau satisfies all three properties. The conditions for being a topology. And from the defining property of tau, it is clear that B is a basis for tau. So here is an exercise. Let X be a set and let tau be a topology on X. Let B be a basis for tau. Then B satisfies the two conditions in the preceding proposition, in the previous proposition. Thus, we may use the previous proposition to define a topology on tau, on B, sorry, on X, which we shall denote by tau sub B. And as expected, show that tau is equal to tau sub B. Okay. So now let us make some remarks. We already checked that intervals of the type a comma b form a basis for the standard topology on R. Thus, using the above exercise, we see that the standard topology can be generated as in the proposition by taking the collection of intervals as basis. So, a similar remark applies to the standard topology on R2 or Rn. We observe that the sets B epsilon x bar form a basis for the standard topology and then using the exercise we see that the standard topology can be generated from these as in the proposition. So we will end this lecture here.